use TCP. Application that use TCP. I've showed you those applications. So let's talk briefly about UDP. So I've talked about UDP for you guys. I've summarized UDP, no acknowledgement, but it's very fast. In fact, this is a summary of the UDP. Let me show you. There's a slide there that summarizes everything. See them here. Everything you see here, that's a summary of the UDP. Everything you see here, that's a summary of the TCP. Case closed. Case closed. So let me show you some other stuffs. So many things that are here again that are lack of repetition. So like look at this one now. Data is reconstructed in the order that it is received. That is for UDP. Any segment that are lost are not resent. UDP does not resent segment. There is no session establishment. That's why we say it's connectionless. The session then is not informed about the resource available. There is no flow control. UDP majorly is just the opposite of TCP. And this is your UDP header. And I've talked about that. You can't see acknowledgement there. You can't see sequencing there. When you see something like this and they are particular about the port number, source, and destination, you know that is your UDP header. And here they are talking about UDP source port number again and destination port number again, which we have mentioned earlier. It's still the same thing. And of course, look at the application that use UDP. DACP. When you get an IP address automatically, that's an application layer protocol. It uses UDP. DNS, of course, DNS can use both. You use UDP. SYN-ACK is another protocol that uses UDP. TFTP, voice over IP, video conferencing, they all use UDP. That means we need them to be fast. That's why they build them on top of UDP. And of course, all of them must run on top of IP. Don't ever forget that. And this is what we talk about interaction of protocols when we started this journey. Don't ever forget that. All of these protocols that you see, they built them. The people that built them, that designed them, they know that they have to indicate whether this is going to run on TCP or is going to run on UDP. Now I need to talk. I've mentioned some port numbers to you guys already. Port numbers is just to tell us about the service you are requesting for and to separate the communication. So let me show you the popular port numbers. And I told you, of course, when you talk about a socket, what is a socket? A socket is just a combination of IP address, source IP address, source port number, destination IP address, and destination port number. That combination is used to build what is called a socket from source to destination, depending on where you are going to. So if I launch a browser now, I'm on Yahoo, I'm on Facebook, I'm on Google, I'm on CNN, I'm going to a different website. Different socket will be created between me and those websites. Let me show you guys. Let me show you again. You know, I like to demonstrate things because this thing works. So I'm going back to our command line, guys. Let me say net start. That's a command. If I hit net start right now, what I want this thing to do for me is to show me the list of all the port numbers that are open, source port, destination port numbers, and the established connection. I think let me see -n. I don't want to go into too much talk on this. Let me pick one of the numbers or two. Let's pick all the ones that are established here now. Take a look at the IP address. 192.168.38.75 : did you see that? 49983. That's a source port number there. If you look at the other side, 173, that's the first one now. 173.23.243 rather, .0.150:443. That's the destination port number. That is a particular website here. My computer is going to a particular website, and this is the socket created. The socket is a combination of source IP address, source port number, destination IP address, destination port number, to establish a connection with a particular website. If you come down again, my computer is on another website again. Same IP address, different source port number. different destination IP address, the same destination port number, because that's a different server entirely. If you come down again here, you see another one again, same IP address, different source port number, different destination IP address, the same source port number, because it's all about HTTP, 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 HTTP. I can dig further in this list. For instance, now I have WhatsApp on my laptop. I can launch my WhatsApp and come to this place. You will see the port number my WhatsApp is using to connect to the WhatsApp server. I have a writing pad that I'm using here. The writing pad can also be on the net. You will see the source port number, the destination port number that is using to connect, especially the destination port number. The source port number are generated dynamically, and it can be any number between, you see the range as we proceed. I think 1 to 6,500 or something like that, or from a particular number. I can't remember the range. This is what we call a socket. The IP address is added at layer 3. You all know that already. Source port IP address, destination IP address, source IP address, destination IP address. But what about this port number? Source port number is added at layer 4. Destination port number is also added at layer 4. What's the big deal about port number? Tell me the service you are requesting for. That's the destination port number. So when my computer gets to that website, that destination where it's going to, maybe it's Yahoo, maybe it's CNN, maybe whatever, he places demand on that server. Give me HTTPS request. I need a web page. I want to peruse, I want to browse this site. That is how this thing happens behind this thing, guys. There is no magic in this thing. These things, they are explainable. Thank you, Doctor. Mr. Uche. They are explainable. And that is why, by the time you come to do cybersecurity down the road, this is one of the ways you can find out, do I have a stranger on my system? Because there is no how that you are going to have a virus on your system, and the virus is established to what we call command, what's that, CNC? Command on what? For command on something, I forgot. That's when you establish a connection with the bad guys controlling the system remotely. There is no how the system will not show you that somebody is on the system. It's like you are going through the scanner. You will see from here. So if you see any service you are suspecting or you don't understand from here, if you're doing cybersecurity, you're going to see some of these things. You can now probe that service further. Or you see a port numbers you don't understand. What's this port number doing? Who is owner of this destination IP address? Then you can copy that IP address out. You copy the port numbers out. You go and research it. Then you know whether you're being hacked, whether you are possessed with virus or not. That's what I want to show you guys. Command and control. Thank you, Adolf. Command and control. Thank you. So that is what I want to show you guys there. You need to understand. So this thing works. Now I've talked to you guys about a few commands now. How to check your IP address, your MAC address, your IP address. Now, this is another command to check the port number, source port number, destination port number. These are things you need to know. It has to be in your head. You need to know it. You need to know it. These are very important stuff. Layer 2 address, layer 3 address, layer 4 address, or layer port numbers. Without those things, the message is not going anywhere. They have to be on your message. Look at it here again. You have source port number, source MAC address, destination MAC address, source IP address, destination IP address, source port number, destination port number. All these things you are looking at, they must be present on any message, going from any place to any place, anywhere in the world. And of course, look at this one now. Port 21 is our destination port number. What does that mean? It's an FTP connection. This person is trying to download. If you are hacked, how do you know what the enemy has done on your network? The port number will tell you. If you see port 21, that means they are downloading confidential file from your organization. There is no service they will place demand on that you are not going to know. Even if they change the port number, you can go beyond the port number to see the services or what they are doing with your organization's data. So don't ever forget that. This is where I'm trying to get to. Well-known port number, all those port 20, 21, 53, and all of that, they are within the range of 0 to 1023. Those port numbers are called well-known ports. But from 1024 to 49,151, they are called registered ports. For instance, if you're a programmer now, you want to use a particular port number, you may have to go and pay for a registered port. And guess what? Dynamic ports, those are the ones that our computer generates automatically for the source port number. They are within the range of 49,152 to 65,532. These are called dynamic ports. So all of these things are standardized. You need to know that. And the dynamic ports are also called ephemeral ports because they are there temporarily. You change website, you close that site, you open another site. That same port that was assigned to maybe CNN, you're going to be assigned to Yahoo later. It's not a constant thing. But the destination port number is very important. We need to see what is going on. So these are all the well-known port numbers, very popular all around the world. 21 FTP, 22 SSH, 23 Telnet, 25 SMTP, 53 DNS for DCP, 67 and 68. FTFTP, HTTP. These are well-known port number. HTTPS. They are well-known port numbers all over the world. And I've just demonstrated this to you guys. Anytime you say established, that means your computer is logged in to a particular website. You can see the IP address of the computer, source port number, destination, or I prefer this one, destination IP address, then the protocol. My own, I added N so that it will show me the IP address of the destination in numbers. I don't want to see their domain names because I can run this command with different parameters. I can add N, I can add B. I think there is A and there is O and a other, depending on what I'm trying to see. These are some of the things we take care of in cybersecurity. So that is just a summary on that. TCP communication process. I've talked about this already, but I have a place I'm going to. I'm going somewhere. I want to show you guys something as regards to TCP. Okay? So what is the big deal here? If a server is running more than one services, it's running on port 80, it's running on port 25. I've explained this. How will the server know what you are requesting for? It is your destination port number that will indicate that you're looking for port 80 service, or which is HTTP rather, or you are looking for SMTP, destination port number. So you are the client. When you send your message, all the server needs to do is to check your destination port number. It's like you enter a restaurant, they give you menu, you click a particular menu. So destination port number shows or points to the service that you are requesting for. That is just a summary of this part here. So you can request for more than one service. It has to be one service. A server can answer more than one service, maybe 2 services, maybe 3, maybe 4, depending on how they set up the server. So the source port number will be dynamic, but the destination port number will be specific. It will be a well-known port number pointing to a particular service. I want to talk about something here, and it's very important. I wanted to say any question because I got used to forcing and allow my students to ask questions. But over time, I noticed that students are always, they don't mute themselves. They make things difficult in between. That's why I stopped that. Even I'm trying to review that. I want to see if I can teach for like 30 minutes, pause, and then give room for question, continue, another 30 minutes, pause, instead of just finishing everything. But I will see how that will go. So this is very important, guys. We want to talk about TCP connection establishment. How does the computer connect when it's using TCP? Now, when I say this is important, I'm talking, you need to know this as a CCNA person, and you also need to know this if you are going to be doing cybersecurity. This is very important for you guys. So follow me, and I'm going to play a video for you guys as well. I think 1 or 2 videos. So if this computer needs to set up a connection with this computer, they want to talk and they are using TCP, what is going to be the steps they're going to take? Number 1, the initiating client requests a client to server communication session with the server. Step 2, the server acknowledges the client to server communication session and request a server to client communication session. Step 3, the initiating client acknowledges, sorry guys. The initiating client acknowledges the server to client communication session. I think there's a mix up here, but let me just explain this. If these two computers want to set up a conversation, before they lock themselves up, what I mean by before they set up that socket, they are going to have to establish connection between themselves if they are using TCP. They are going to have to establish a connection. So in establishing a connection, something is going to happen. This computer that I want to talk will send what is called a SYN-ACK. SYN-ACK is like a big beacon. I want to talk to you. I'm sending a SYN-ACK to you. A SYN-ACK. A SYN-ACK is like a beacon, something like a beacon I send to you with a particular sequence number. Because from now on, our conversation is going to be numbered. So I'll send you a SYN-ACK with a sequence number. When you receive that SYN-ACK with the sequence number, you send me your own SYN-ACK, please take note, with an acknowledgement, meaning what? This is my own initial sequence number, or let's say this is my SYN-ACK with my sequence number, and you know what? I am acknowledging what you sent. What are we trying to do here? The two systems want to set up a TCP connection. You're going to see it in another slide. We call it, it's like a three-way handshake. Three-way handshake, actually. So before the two of them have, somebody has to initiate the connection. So I will send you my SYN-ACK with my initial sequence number. You will send your SYN-ACK and an acknowledgement number, and then I will acknowledge with a different number. So what is going to be in that establishment, or how are we going to set up that establishment? I will send an acknowledgement to your own SYN-ACK and send another sequence number. It's like, okay, this first message I'm sending to you, this is the number. You send me your own message with the message number and let me know if you got my own. The video will drive my point home better. I like the way they put it in the video. Don't let us come to session termination first. Let's go to three-way handshake. Let's watch the video and then we'll come back here. Three-way handshake is what I'm trying to explain to you guys. Before computers can establish a TCP connection, they need to have this three-way handshake established. And guess what? The bad guys can take care of this. I mean, they can take advantage of this and use it to hack into our network or to cause trouble on our network. Let's go to one or two videos on three-way handshake, and then we'll come back. I think that's the most important thing we need to do today. A few minutes, let me get the video out. Yeah, three-way handshake.
I have some screenshots of a Wireshark packet capture that shows the process of a TCP three-way handshake.
Please, can you people hear that video? Let me get your thumbs up. Okay, good.
And the termination of a TCP conversation. Let's analyze these screenshots to get an idea of how it's working. TCP is a connection-oriented protocol, meaning an end-to-end connection needs to be established first before data can be sent or received. The TCP three-way handshake initiates that connection. When the connection finally needs to be terminated, for instance, let's say it's a connection to a web server and you close the web browser, the connection is terminated with two-way handshakes. A TCP three-way handshake involves three steps: a SYN and an ACK, and an ACK. SYN stands for synchronization, and ACK stands for acknowledgement. First, the initiating host sends a synchronization segment. The responding host sends an acknowledgement and its own synchronization segment, and then the initial host sends an acknowledgement segment. Hence the SYN and an ACK, and ACK. We can see that here at the top of this screenshot. If we look at the packet list window, at packets 10, 11, and 12, we can see a SYN and an ACK, and an ACK. This is the three-way handshake. If we look at the initial packet in the three-way handshake, the SYN segment up here at the top, we can see that the sequence number is 0. The beginning of a three-way handshake is sequence number 0 because it's the first packet in the connection or conversation between two hosts, or in this case, a host and a server. The sequence number is actually a 32-bit random number called the ISN, or initial sequence number. This random number, or ISN, is chosen randomly at the beginning of each TCP conversation. This helps to protect against TCP connection hijacking attacks. Wireshark takes that 32-bit random number and converts it to 0. It then increments the sequence numbers and the acknowledgements from there. This makes it easier to read and follow the segments in order using the Wireshark program. Let's look at a few of the details for this initial SYN segment. We go down to the packet details window and we can see sequence number 0, that it's the relative sequence number. If we look at the flags, we see that the SYN bit has been set. You can see it here with a 1. In the next packet, packet number 11, the server responds to the initial synchronization segment. I'll go to the next screenshot, and now packet 11 is highlighted. The server responds with an acknowledgement acknowledging sequence number 0 and sending acknowledgement 1. So the initial sequence number with relative sequence number 0 has been incremented and acknowledgement 1 has been sent. We can see in the protocol details window acknowledgement number 1 and that it's the relative ACK number. The server has also sent its own synchronization segment, and that number is 0 since it's the initial conversation going the other way. If we look in the details window, we can see that the sequence number is 0, and that's a relative sequence number from the server to the host. If we look here at the flags, both the SYN bit and the ACK bit have both been set. If we go to the next screenshot, in packet 12, which is step 3 in the three-way handshake, host 10.1.1.1 responds with an acknowledgement or ACK. And if we look in the protocol details window, we see the acknowledgement number is 1, incrementing the server's synchronization segment by 1. You can see here that the acknowledgement bit has been set, but notice that the SYN bit has not been set. This is the final phase in the three-way handshake. Let's take a look at how the TCP connection terminates. I'll go to the next screenshot, and you can see in packet 16, the server is communicating to the host at 10.1.1.1 and has sent a segment with a finish or FIN and an acknowledgement or ACK. In this segment, we have a FIN and an ACK. The FIN ends the conversation. The acknowledgement flag has been set since the three-way handshake was first established, and in every segment sent thereafter, the acknowledgement flag is set. You can see that in the next packet, packet number 17, the host has replied to the server with an acknowledgement acknowledging that the conversation has ended. This is a two-way handshake, a FIN and an ACK and an ACK. If we look ahead in the packet list window to packet 18, you can see that host 10.1.1.1 then sends the server its own FIN and acknowledgement, and then the server replies with its own ACK. So you have two-way handshakes to terminate the connection. If I go back to the previous screenshot and take a look at the protocol details or the packet details, we can see here in the TCP segment the flags. Notice the 1 for the acknowledgement and then the 1 for the finish or FIN flag here that's been set. Notice that the acknowledgements went as high as number 374, indicating that these screenshots were probably generated from two separate packet captures in Wireshark. You can see in these last two screenshots how the conversation ends with two two-way handshakes, a SYN and an ACK and an ACK, and then another one going the other way.
So now that is one of the videos. We're still going to go to
I have some screenshots
explanation
of a
again.
Wireshark packet capture.
So I'm going to explain some things more there, but I need you to understand. That is one of the things I've been talking about. Thank you, guys. When you use Wireshark to capture a packet, and this is possible, that's one of the things the bad guys use. We also use Wireshark in the feed, meaning you can analyze the packets at layer 2, layer 1, layer 2, layer 3, layer 4. So what we are trying to deal with right now is, okay, if the two computers need to establish connection and they are running on TCP, there must be the process of three-way handshake. But do you know what? The three-way handshake can also be used by the bad guys to cause trouble. It's like, I want to talk to Uche right now. I call his line, he picked the line, and I refuse to talk. I call first, that's my first way handshake. He picked it and said hello, second way. I'm supposed to reply back and say, yeah, Uche is Roland is talking, but I decided not to talk. Then I called on another line. I'm just keeping him busy, meaning I will never complete that three-way handshake. That's an attack there. The bad guys use that too. I'll never complete the three-way handshake. They can do that to a server. So if you use Wiresharks to grab what is going on your network, and you are saying that, come, somebody is starting three-way handshake conversation and is not finishing it, there's a problem. There's some problem somewhere. Then you can see that you're under attack. So there are so many applications of this knowledge that we are having now. We are learning right now. We're getting in the class right now. Three-way handshake is one of it. We have 2 or 3 more videos we're going to explore before we now come back and finish this. TCP, reliability. We talk about reliability, sequence number and acknowledgement. Let's check the video on this.
This video depicts a simplified example of TCP operations and is not necessarily a realistic depiction. TCP is a connection-oriented protocol in that a connection is established first using a three-way handshake before data is sent. Another characteristic of TCP is that it's a reliable protocol. 2 things that make it reliable are sequence numbers and acknowledgements. Every TCP segment that's sent in a TCP conversation gets a sequence number. So every byte of data is numbered basically in a sequential list. This allows a receiving host to rebuild the data from the ordered numbered segments. If data arrives out of order at the receiving end, the data can be put back together in the proper order thanks to the sequence numbers. Acknowledgements come into play by helping the sender know that the data that's being sent is actually being received. The way this works is the sending host sends TCP segments in bytes, and the receiving host acknowledges bytes received by sending acknowledgements. There is a limit to the amount of data the sending host can send before it receives an acknowledgement from the receiver. This amount is called the window size. The window size is the total number of bytes sent in TCP segments that can be sent before receiving an acknowledgement. Using TCP window scaling, computers are able to achieve large window sizes of up to 1 gigabyte. So as the sending host sends bytes of data in TCP segments, the receiving host returns acknowledgements as it processes bytes received and frees up its buffers. We can see this depicted in this graphic. Let's start by reading the message from the sending host here. Start with byte number 1, I am sending 10 bytes. In this scenario, the 10 bytes is the window size. In reality, the window size would be a lot larger than 10 bytes, since today window sizes are typically 16 megabytes or larger. But this works nicely for this example. So the host is sending 10 bytes, starting with byte number 1. The receiving host, the server here, says, I received 10 bytes, starting with byte number 1. I expect byte 11 next. This is the acknowledgement. The server acknowledges it received the 10 bytes and now is expecting number 11. If we look down here, we can see that in this segment, starting with sequence number 1, 10 bytes have been sent. The receiver sends an ACK 11. Starting with 1, 10 bytes were sent, so the next sequence number it's expecting is an 11. This acknowledgement is sent back to the originating host. Now the originating host sends 10 more bytes starting with sequence number 11. If we were to ask ourselves what would be the next ACK that the server would send back to the originating host, we would have to ask ourselves what's the last sequence number sent. Starting with 11, 10 bytes were sent, so the last sequence number that was sent was 20, so the ACK would be an ACK 21. That's the next expected sequence number. You can see how sequence numbers and acknowledgements, including the window size, make TCP a very orderly and reliable protocol.
I hope we can see what I've been talking about TCP. TCP is reliable, guaranteed. You see how it works. Let's check another one and see. That will be the last, should be the last one today. That should be the last one today.
This video depicts a simplified example of TCP operations and is not necessarily a realistic depiction. TCP is a connection-oriented protocol in that a connection is established first using a three-way handshake before data is sent. Another characteristic of TCP is that it's a reliable protocol. Two things that make it reliable are sequence numbers and acknowledgements. Every TCP segment that's sent in a TCP conversation gets a sequence number. So every byte of data is numbered basically in a sequential list. This allows a receiving host to rebuild the data from the ordered numbered segments. If data arrives out of order at the receiving end, the data can be put back together in the proper order thanks to the sequence numbers. Acknowledgements come into play by helping the sender know that the data that's being sent is actually being received. The way this works is the sending host sends TCP segments in bytes, and the receiving host acknowledges bytes received by sending acknowledgements. There is a limit to the amount of data the sending host can send before it receives an acknowledgement from the receiver. This amount is called the window size. The window size is the total number of bytes sent in TCP segments that can be sent before receiving an acknowledgement. Using TCP window scaling, computers are able to achieve large window sizes of up to 1 gigabyte. So as the sending host sends bytes of data in TCP segments, the receiving host returns acknowledgements as it processes bytes received and frees up its buffers. We can see this depicted in this graphic. Let's start by reading the message from the sending host here. Start with byte number 1, I am sending 10 bytes. In this scenario, the 10 bytes is the window size. In reality, the window size would be a lot larger than 10 bytes, since today window sizes are typically 16 megabytes or larger. But this works nicely for this example. So the host is sending 10 bytes, starting with byte number 1. The receiving host, the server here, says, I received 10 bytes, starting with byte number 1. I expect byte 11 next. This is the acknowledgement. The server acknowledges it received the 10 bytes and now is expecting number 11. If we look down here, we can see that in this segment, starting with sequence number 1, 10 bytes have been sent. The receiver sends an ACK 11. Starting with 1, 10 bytes were sent, so the next sequence number it's expecting is an 11. This acknowledgement is sent back to the originating host. Now the originating host sends 10 more bytes starting with sequence number 11. If we were to ask ourselves what would be the next ACK that the server would send back to the originating host, we would have to ask ourselves, what's the last sequence number sent? Starting with 11, 10 bytes were sent, so the last sequence number that was sent was 20, so the ACK would be an ACK 21. That's the next expected sequence number. You can see how sequence numbers and acknowledgements, including the window size, make TCP a very orderly and reliable protocol.
So guys, I think that's all I have for you. Thank you, Mr. Oche. So
This video depicts a simplified
TCP for you. So you need to know that TCP is very, very reliable. And these are the reasons why TCP is very reliable. So I don't have anything to add to this. That's a big deal. That's the main thing we need to talk about TCP. Reliability and flow control. How is guaranteed and order delivery, because it has to arrange them when it gets to the destination, and you've seen the sequence number and acknowledgement that helps this reliability issue. Data loss and retransmission. If data is lost, any segment is lost, TCP will retransmit it back. And then that is one of the reasons why it is reliable. So you can watch this video more and then read through any other part of the content, the curriculum. UDP, of course, we don't have any other thing to say about UDP. There's a lot of repetition here. UDP has low overhead. So what about reliability? When there's a need for reliability, application layer takes care of that for UDP. There's a need to help to resolve a problem. Application layer takes care of that one. So UDP does not have any business with reliability. It's just because the main aim of UDP is speed. The application needs to be fast. And you have seen all the ports, all the services that run on UDP. So that is where we're going to draw the curtain today. If there's any question, I'm going to give room for question now.